Recording in
No, anyway,
progress.
welcome. It's good to have you all back. Okay. So for today, first off, I want to catch up on a few orders of business for the class. First off, thank you for your patience. I've been needing to get a lot of materials to you sooner. Unfortunately, the beginning of the term is like the worst time to get sick, because we're trying to prep all the materials. But I think I've got it all up to speed now for you all. Okay. First off, I want to cover the Canvas page. So everyone here in the room is able to get all the Canvas announcements, right? Okay. Michigan folks, hello. I know that some people had some issue getting Canvas announcements, and we've been working frantically to get that working. I believe Rahul has sent out, your TA has sent out instructions for how to get that working. And DJ, you want to just sort of reiterate what the instructions were real quick? Come up here. You can come up here. Yeah. Yeah. I have Canvas up. I can pull it up for you.
Okay.
Yeah.
I just need to point out like one other thing.
Okay. So hopefully you all can see the Canvas page right here with this beautiful logo. I don't know who made, but
This computer?
it's right
this
here.
one.
Yes,
Okay.
right.
Yeah, so to fix the email announcement problem, you just go to your account, go to settings, and on the right here, you can see Dr. Ubicki's his main email that's bold and black. That's already verified. This second email looks like it's not verified. So I don't know if you get it.
Both those emails go to the same place, so I'm good.
Oh, okay.
I'm good. All right.
But anyway, if your email looks blue like that, you can click on it. It'll tell you to confirm your email address. You hit resend confirmation and do whatever the email tells you. That should fix your problem.
I set that up just for you so you could announce, set me up for both email accounts. So yeah, thank you. So, so if you have any questions about how to set that up, please feel free to email Rahul, who will know how to get you set up, or you can email DJ or any other of the TAs, but Rahul will be your closest point of contact for that. Because my hope is then you can have access to all of the course information. So just to take a quick second to go through what we got going on in the course right now. Hopefully you're all seeing, okay, the course homepage. The blue logo is the hint that you're in the right place. Look at that. Okay. All right. So this is where you get your Zoom links. As you know, I want to announce that my office hours are now currently set. Okay. As are our TA office hours. So my office hours are Monday, Thursday, 1 to 2 p.m. I'll have them in AME in this building for you all. Okay, you come visit me in person. I'll also have the Zoom window open, and I'll do a really funny routine where I talk to people on Zoom and you at the same time. It'll be really entertaining. Okay, all right, if people want to join. So you can either so it means you can either join from home or you can join in person, whichever you'd like. Okay. TA office hours are all put up here. Rahul has put his Zoom link for his University of Michigan Zoom link. David J. and Nick will have their office hours in person over in AME 109. So you can meet them in person. That's the robotics lab right down the hall. Okay. So you can see this course schedule. You can see our course materials, including very helpfully links to videos of the lectures. Okay, I have the Zoom recordings here, which I'm continuing to improve in quality, and I have high quality recordings that I'm just trying to render out of Adobe Premiere. So on Tuesday, unfortunately, I was ill, so I instead, by luck, just for you, recorded a lecture on linear programming. Who has seen at least some of the lecture on linear programming that I put out? Okay, all right, okay. Here it is right there. It is the last lecture you need for your homework. Okay. These lectures, these three, should be what you need for your homework. Okay. Which is done in MATLAB, which we'll talk about in just a second. So if you have never used MATLAB before, I'm sure all of you have. Okay. If you've done any kind of coding before, I have made an introductory lecture to MATLAB. Okay. Glad to hear it, Aaron, by the way. I see your message. I have at the bottom here these optional tools lectures. I sometimes do this during my class where I'll get enough questions that I say, okay, I'll stand in front of my home whiteboard, which every professor is issued. Okay. And I'll give a lecture. I'll go to my computer, and basically it's introduction to all the basics of MATLAB. If you've never used it before, if you're a C++ person, if you're a Python gal or a C++ guy, all right, this is what you need to know to get started with MATLAB. So I recommend downloading the most recent version of MATLAB with the optimization toolbox, okay, to get started. So, so I recommend watching this if you haven't used MATLAB before and you want to do it for the homework, okay? All right. So in terms of upcoming deadlines, let's go here. Oh, and let's see what else is going on. Okay. Anything else? In terms of upcoming deadlines, so key course deadlines. Okay. The first thing is a quiz that's due Friday at 5:59 p.m. Okay, it's on Canvas. Now, did any Michigan folks get this announcement about the quiz? You all get the announcement about the quiz. Okay, all right, on Canvas. Okay, all right. Canvas. So it's due tomorrow, which might seem like a quick deadline, but it's a 10-minute quiz, like 15 minutes. All right. It's open note, open book, open online resource. You can rewatch the lectures. You can have whatever open you want in front of it. Just do not collaborate with your colleagues. Okay. And it's 10 multiple choice questions. If you want to know how to find it, it's on Canvas. So you go under Canvas here, under quizzes. Quizzes over there. Oh, look, quiz 1. Clicking on quiz 1. Here we go. Complete it by tomorrow. 10 multiple choice questions. Again, use your notes, use other things, you know, to help you out, okay? Not much math. There's a very little math that you want maybe a pen and paper for. You'll be taking maybe a couple derivatives, but they're not complicated derivatives, all right? But again, not designed to take long. So just get it done by tomorrow. If you have any technical difficulties, email the TA. Okay. All right. Any questions about the quiz? All right. That way we do it, you know, instead of early in the morning, do it when you feel like it. Okay. All right. That's the quiz. All right. So the homework 1, I'm extending to Tuesday at 5 p.m. Okay. The reason I'm extending it is because it's the first assignment, even though it's not designed to be very difficult. Okay. It is using a MATLAB auto grader. Okay. This is something that we haven't done here. I haven't done here before, but it's a great way to just automatically get you your scores back as quickly as possible. Okay. And guess what? You get the answer right. 100. We'll have a mechanism for partial credit. So it's not 100 or nothing, but in order to know how to use that, we're going to go back to Canvas, go under assignments, homework 1. Right here. So David J has kindly wrote a nice example of how instructions as to how to run a MATLAB live script. Okay, if you're doing this course, if you're doing the homework in MATLAB, you want to download this MLX. If you use MATLAB, you know what a .m file is. MATLAB live script is like a script, a normal script in MATLAB, but when you execute commands without a semicolon, instead of just spitting out stuff to the command window, it'll actually maybe show you the math on the screen and stuff. Okay, it's pretty handy. It's like a notebook. People have used notebooks with code before. It's like that for MATLAB. It's super handy. And your TA Rahul, for those of you who want to do the Julia version of the assignment, use the Julia programming language. Okay, there's a Python. There's a notebook version for Julia that you can use as well. So we've done this assignment in two different languages for you. Okay, if you intend to do this assignment in C++ or some other language, please contact me and or come to some arrangement, okay? I feel like I'm being generous in allowing that, but if, in which case, but if you want to learn it in a different language, that's fine. We got to work something out though. So it's reasonable for us to grade. Okay, cool. And here's the PDF of the assignment. Okay, let's open this up. Hope I can open this up. Preview. Here we go. Here's the assignment. 5 questions. 5 questions. Problems 1 and 2, and they're all based on linear programming. That's the lecture I put out on Tuesday. Okay. Problems 1 and 2 are for everyone. Okay. They'll be about setting up linear programs and using MATLAB to solve the linear program using linprog. And there's a few plotting components of the homework. Okay. You want to be able to plot the lines and the constraint cuts like I talked about in the lecture that I drew on the screen. Okay. Problems 3 and 4 are for grad students only. Okay. You want to do them as an undergrad? I may or may not come up with some kind of partial credits, extra credit scheme. Okay. In the past, I've done it. I just haven't figured out exactly what that would be. So if you're feeling ambitious, I might find a way to reward it if you're an undergrad. Okay. And there is problem 5 here called the Pentagon. It's Pentagon. Look at that. Okay. All right. Nifty. It's Pentagon. Okay. They're all linear programming problems based, and you should have everything you need to know how to do it from the first 3 lectures, particularly lecture number 3, and they're all on YouTube. Okay. Any questions about the homework or the quiz so far? Okay. All right. We're good. We're good. All right. Now the projects. Okay. If you haven't gotten your project groups to me by now, please do so. I know some students indicated they wanted a random project group. I still need to pair those folks up. I'm going to extend the project ideas. 1 second here. So say get project groups to Nick/Rahul ASAP. Okay. And then I'm going to extend, and in order to give you time to talk about your project ideas a bit more, okay, I'm going to extend project ideas to Monday at 5 p.m. Again, so what all this is, it's 2 sentences about 3 project ideas. Okay. All right. So that's the project update. Okay. I hope we get these project ideas together because that way I can give you feedback on an idea that works and we can write a brief proposal about how we're going to get that to work. Okay. All right. Any questions about any of this stuff? A lot of course updates. Thank you for your patience. How are we doing on time? All right. Thank you all. Okay. For our next bit, I want to change subjects a bit to this video here. Now, I want to know if the folks on Michigan are going to hear this video playing. Let's see. Let's see. Can I hear it playing? I'm not sure I can. Okay.
This
I'm not
video
sure that
should
we
in
can
many
actually hear
ways
the
look
audio, so instead
familiar
you'll have to
to
just
those
sort
who've
of
seen our
watch it.
videos in the past.
And
But it's meant to communicate an expansion of the research that we're doing
so
on
you can-
Atlas.
oh, you
We're
can
not
hear
just
on that side.
thinking
Okay, we
about
can't overhear,
how
so
to
I'm
make the
gonna- it's
robot
got
move
music.
dynamically through its environment like we did in parkour and dance.
with this kind
Now
of
we're starting to put Atlas to work and think about how the robot should be able to perceive and manipulate objects in its environment while maintaining that characteristic high level of performance that we expect from Atlas. In order to do that, the robot has to be able to think about the properties of objects,
and he
their
wrote one of the
shape,
seminal
their
papers
mass
on
properties,
online
and as it's
optimal
manipulating
control
these
techniques
objects,
for humanoids.
the
And
constraints
after
that exist
which he
between the
was
robot and the
hired for- at
object, the
Harvard
forces that
and then
exist,
hired at
and it has to have a
Boston
control
Dynamics
system
to be
that's
one
able
of
to
their key
balance what
controls
may be
developers
competing
here for
objectives
this
related to
recent video, which shows
stability
Atlas
or
now
the
picking up
manipulation
stuff.
task at
The new
hand.
thing is Atlas
My
can pick
role
up
in the
stuff,
project
chuck
was
stuff
working
around,
on
push
perception
it,
and
push it
autonomy.
down.
So perception is letting the robot know what it's seeing,
and they're
and
including more
autonomy is letting
visual
it choose
perception
what it's
into
doing next at a high
Atlas.
level. where
And there's
it's
a
gonna
lot
go
of
and what it's
mystery,
planning
I
to
think,
do.
in the public.
It's all
Like,
software,
oh
so
my
we were
goodness,
writing
how
code
is
that
already
runs
the
on
Boston
board
Dynamics
Atlas, and
doing
it's got computers
all
on
of these
board that are
cool
processing the
videos,
camera data
right?
so that it can see the objects in front of
Okay, you
it.
can
In
hear
this
me over it.
video,
I'm sorry.
we're doing a lot of
I'm gonna
object
mute
manipulation,
my
lifting
video.
this
I don't know
piece
how to
of
do
wood,
that here.
placing it down, lifting up the tool bag, and eventually jumping and trying to throw it precisely up.
I'm sorry, Michigan folks. Let me get this. I'll just change that. I don't know how YouTube works. Okay. All right. I paused it so you can hear me for a second. There's been some mystery as to how Boston Dynamics does this. So I'm going to play I'm going to play the clip a little bit so you can all see it.
Onto the top platform.
So Atlas has a couple of cameras that we use
Now,
to,
here I
to see
want
the world
to-
around it. And they work not entirely unlike
I'm going to highlight a particular aspect here and jump forward to about here.
The grippers making the grasp around the bag like that.
So the way that we approach this problem is a technique called model predictive control. And the idea is that the robot's
There
control
we go.
system should be able
See
to
that for a
think
second?
about how the problem
So the way we approach this problem
is
is a technique called model predictive control.
And the
Okay. We talked about this before. The way we approach this problem is a technique called model predictive control. All right. So basically, this has been kind of an open secret, I think, for a while at the robotics conferences. I would hear and talk to people at Boston Dynamics as how they control Atlas. Okay. And basically, it's really fast online optimization. The exact same stuff we covered in class. Okay. Anyone here willing to answer a question about the linear programming lecture that I posted on Tuesday? Anybody? Okay. All right. And you're all going to volunteer for a question that I haven't asked yet. Okay. All right. No, someone can jump in on this question. What was one of the reasons? What is linear programming? Is it fast or is it slow? Really fast, right? What's one of the reasons that it's really fast? Just like in a word, like what about it makes it fast? It's convex, right? Meaning that it's got, meaning that it has, that if you imagine its cost function, it's shaped in such a way that if you do a local search down a gradient, it's going to lead you to the best solution. Okay, it's not going to get caught in any nooks and crannies. Okay, and you can follow the constraints down to the bottom for the lowest cost solution very quickly, right? Okay, that's a linear program. All right. Now, in robotics, we also want convex optimizations a lot of the time because they are a fact. Because they can solve reliably and they can solve quickly, depending upon the type of convex program. Okay, they will always be able to solve reliably, but depending upon the type, very quickly. Okay, so convex. So convex optimizations are useful in control because they are reliable to solve and often fast to solve. Okay, so linear programming we talked about. This means things like linear programming, LP, it's always convex. Okay. And what are the features of a linear program? Okay, maybe in words, someone tell me what a linear program is. Anybody? Can be anywhere from anywhere in the world or in this room.
Linear cost function and linear
Non-optimization, does it have, how would you describe its cost function for a linear program? Thank you. It's linear, okay? So it's got, so the linear cost function, okay? What about its constraints? Can it have constraints? Yes, it can. What can we say about those constraints in a linear program? They're also linear. Thank you, Egwu, for being awake this morning. I appreciate it. You being the one answering the questions. Thank you. Yes, and thank you very much, Elena. I see that as well. Thank you for joining. Linear constraints, right? Okay. The thing I love, so imagine, so let's look at our example. So we're going to come up, so let's have a program, X star is equal to arg min X of, call it X2, such that it obeys the constraint that X2 must be greater than 1 minus X1 and X2 must be greater than or equal to minus 1 plus X1, where your decision vector is X1, X2. Okay, that's the example that we had, right? And I love this. I love looking at these graphically, where you plot your decision variables on some axes, X1 and X2, right? Okay. And I'm going to draw little arrows that indicate which way it has descending cost, okay? Now, which way on these axes would have descending cost? Would you have descending cost to the left, to the right? Okay, DJ is indicating down, okay? Down, because X2 is up, and you want to minimize X2, so you want to go down, right? So I'm gonna do little arrows, doop, 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 in blue. Sound effects are optional, okay? Okay. All right, now I'm gonna add my constraints. Okay, I'm gonna draw those, okay? So I'm gonna draw constraint lines that are at the boundary of these inequality constraints, okay? So I'm gonna draw the line X2 equals 1 minus X1. Oh, no, what did I do? Okay. Yeah. I want this guy. So here's 1. I'm going to draw it there. So X2 is equal to 1 minus X1. So it's going to be a slope of minus 1, intercept at positive 1. And then this other line, intercept at minus 1. Positive X1, so intercept at minus 1. Okay. Right? Following me so far? And I have to be above or below that line? I gotta be above it. Thank you. Yeah. Look, you're all paying attention. Look at that. Early in the morning, no less. Thank you. Yeah. All right, gotta be above it. So you can't be below it. I scratch that out, right? Gorgeous, gorgeous. Okay. So graphically, you could solve that problem by saying, okay, what point on this graph takes me the most down, but doesn't go through these constraint lines? Well, it's right there, right? Okay, right. Cool, right? So that's X star. Nifty. Now, the super nifty thing is that in a linear program, it does not matter how many times I draw new constraints. Let's draw new constraints in yellow right here. I could draw a constraint that's like this. Oh no. I want this. Thank you. I can draw a constraint that's like this. I want it to be yellow, but whatever. And another one that's like this. I can have it below it. I'll undo this stuff. This is just for like illustrative purposes. Like this, right? And the problem is still convex, okay? And what do I mean by convex? Now, I talked a little bit about it last time, okay? It's that. So no matter, technology's fighting me. No, cancel. So no matter how many cuts make, it's still convex. That's some of the beauty of linear constraints and linear programming. Okay. You can have equality constraints as well. Do not change convexity. Okay. And the beautiful thing is that it doesn't matter how many cuts I make. You could have thousands, millions. I could have thousands or millions of variables, which I can't draw very well, right? Okay, it will be a million dimensional space that I am not good at drawing, okay? Right? So linear programming is cool. It has a lot of applications in parts of optimal control. It's useful in portfolio optimization. People in finance will use linear programming a good deal to balance how much stock you put in one company versus another company in order to maximize some objective. Those are often linear programs. Okay, so LPs common in finance. Okay. In robotics, we like to talk about, more than that, quadratic programs. Or QPs. Okay. Okay. Quadratic programs have a quadratic cost function and you might be tempted to say quadratic. Who was about to say quadratic constraints in their mind? Be honest. Thank you for being honest. That's what I thought when I heard of quadratic programming. It is not quadratic constraints. It's linear constraints. Something with quadratic constraints and a quadratic cost would call be a QCQP, which is quadratically constrained quadratic program. Now we're talking about quadratic programs, okay? So have quadratic costs, linear constraints, right? This is all in your first chapter of the Boyd text, okay? Which is the convex optimization text. I love the Boyd textbook, okay? Let me give you a general form, okay? Okay. So the general form X star is equal to argmin of X of 1/2 X transpose Q times X plus C transpose X. That's your cost function, right? Okay. And our constraints are linear, so they should look familiar. Such that AX is less than or equal to B, and AEQ X is equal to B EQ. That's a quadratic program, QP. Now, is it convex? Sometimes, not always. Okay. It depends upon these elements here, Q, particularly Q. All right. Okay. So know what these things are. So Q is a matrix that is something called the Hessian of your cost function. Okay, meaning that Q is equal to, which is it's the second partial derivative, not the first, the second partial derivative of your cost function f of x with respect to x. Okay, Hessian. C is actually very similar to linear programming. What was that vector in linear programming? What was that? Anyone remember? This thing right here? It was the gradient. Is the gradient of your cost function I'm going to add that it's evaluated at x equals 0, meaning the 0 vector. Okay, so C is equal to the partial derivative of f of x partial x evaluated at x equals 0. Okay, so what's going to happen is for a quadratic program, this is going to be a matrix of Q is going to be a matrix of constants, and C is going to be a vector of constants. If you don't have constants in there, something's wrong. Either you did your math wrong, or it's not a quadratic program. Okay. All right. And A, B, AEQ, and BEQ are matrices and vectors, encoding linear equality / inequality constraints per Jacobians e.g. in linear programming. So you can reference the linear programming lecture for that. Okay. Or that A matrix is going to be the Jacobian of your constraint vector. Okay. So go back to the previous lecture for examples on that. Okay. Jacobians are on your quiz. Okay. So just remember, I'd recommend having those at the ready when you're taking your quiz. So, okay, now where were we?
Excuse me, Professor? The Michigan students can't hear you anymore.
Can you all hear me? Can someone try to speak to me through the Michigan side?
Yes, we can hear you now.
Thank you so much. I'm trying to keep an eye on the chat. Hopefully it only happened only 2 minutes ago. Okay. I apologize. All right. We'll go with this for the moment. Okay. So, all right. So all I was laying out in the last 2 minutes was the Hessian, right? You lost that Q is a matrix. Oh no. Screen's also frozen. Okay. Okay. We need to get this up on. Okay. Okay, I lost connection with the iPad, I think is what happened. So give me a second here. Courses. In the meanwhile, I'm going to talk to you all, hopefully you can hear me, about why quadratic programming is so important in robotics. So the reason quadratic programming is important is you have that Q matrix, right? That multiplies by X and X, X transpose X. Okay. And a lot of problems in robotics require an objective function that is more or less caring about being close to something, like I want to be close to a particular state, or I want to use as little energy as possible, okay? And a convenient way to say that mathematically is to say, oh, the difference between where I want to be here, okay, and where I am here, I'm going to subtract the two. And then I'm going to square that distance, right? That's quadratic cost. Really handy, right? Also, if you want to care about not using a lot of energy, a lot of battery power, okay? Who here has taken an electrical engineering course in their life? Who has done any kind of circuitry ever? Or who's here vehicles IR? There are people who haven't heard vehicles IR? Okay, voltage equals the current times resistance. Okay, great. Vehicles IR. Thank you. Thank you, right? Okay, all right. Scaring me for a second here. Okay, all right. So, okay, so V equals IR, right? So where I is the current. And that's normally the stuff that's flowing through your motor in a robot, or so that's how much juice it's using, right? And as a result, that's often how much torque it applies, right? So often your torque that you're applying is proportional to that current. Okay. What's the equation for V equals IR? What's the equation for power in terms of electronics? Anyone? In terms of current and resistance, yes.
Voltage times current.
Voltage, P equals IV. Current times voltage, because I just remember P equals IV. Is that cool by you,
Yeah.
Ben? Right? Okay, P is equal to IV. All right. Everyone ready for mental math? All right. Okay. So P is equal to IV, right? P is equal to I squared R. Because if you take that V and put in IR, you get P is equal to I squared R. Don't we love mental math? Yes, we do. Okay. So you have that I squared R, I squared, quadratic. And if that quadratic term, if that current is proportional to the amount of effort, torque, guess what? That I squared R is a quadratic cost on how much effort you apply. Quadratic cost. In fact, you can go into many mainstream robotics papers. If you search robotics, quadratic programming on Google Scholar and pull up what you find, you'll probably find little torque squared terms showing up in their cost function. Okay. All right. And beautifully enough, those things can be focus. Okay, I can't, it's not focusing on me. That's not creepy at all. Okay. All right. There you go. I fixed it. All right, look at that. High-tech solutions. All right, I'm going to go back to here. Okay, we'll fix this up. Okay, so that's one of the reasons that like it's so handy in robotics. So if we can just make those, if we can make sure that the program is convex and solve really quickly, okay, then okay, screen. Hello, friends. Can you hear me again?
We can hear you. We can hear you.
Okay. All right. Okay. Testing 1 2, testing 1 2. Oh, always getting repeated. The mic should be turned on here, but not over here. Yeah, it's not turned on over there. Maybe I'm sharing the audio through a different thing. Goodness. Okay. Let's fix this here. Do share audio. I did it, fixed it. This should fix it. Okay, do we still have repeating audio? Only when you talk, okay. All right, well, I think if you talk, I think I might have fixed that problem, okay? And I think that for whatever reason, I can't hear you through, I know what's going on. Program volume. Can someone try speaking for me on the Michigan side? Testing 1 2. Testing 1 2.
Testing
Yeah.
1 2.
Thanks, Connor, for trying. I appreciate it. Try again, Connor.
Testing again.
Thank you. So if I keep it close, thank you very much for all your patience. We're working out the details here. I can kind of hear you. It's not your fault. It's a me problem. We lost connection with the iPad is what happened. So that's why everything went down. Everyone kablooey. Okay. So, all right. Hessians. This is our Hessian. Everyone see the pattern that's happening here. Okay. All right. You got a little audio. Okay. All right. I think we're going to have to go with just chat-based audio. I apologize, Michigan. So you have to do some chatting, and I have your chat right in front of me. I'll pay close attention. Okay. So back to our Hessian. So we had these matrices, just for recap, for our linear constraints. The Hessian is a second partial derivative of a scalar valued function with respect to a vector. Okay. Yields this matrix here. All right. Of different partial derivatives. So now we're on the second row, second column, which means we have partial f squared, second variable, or as you might say, second variable squared, right? Right? Partial squared f, sorry, partial f squared, squared f, partial second variable, third variable, because second row, third column, right? Then you can continue for all of the things until you have a square matrix. That's your Hessian, okay? All right. We did it. All right. So what I was saying right before the great Zoom snafu of 2023 was, is this, oh no, okay. Is this the same as this? The answer is yes, they are the same. Okay. This is the same as this. Okay, it is a symmetric matrix. And you can try it out for yourself. You know, imagine you had f was equal to x1 squared times x2. X1 squared times x2. Partial squared f partial x1, x2. That's going to be the first one. It's going to be 2x1 times x2. And then it becomes, with respect to x2, you know, you do that with respect to x2. And it's going to be equal to 2 times x1. Okay. And if you were to do partial f squared, partial x2, partial x1, it's equal to x1 squared, x2, partial x2. Sorry. Excuse me. Doing this a little too quickly to catch up. All right. Going to be the partial of x1 squared, partial x1, which is going to then be equal to 2 times x1. So they are the same. That's why it's symmetric. Okay. Once you have a Hessian, okay, this is a big thing. If the Hessian of the QP is positive, semi-definite, then the program is convex. Okay. All right. What does positive semi-definite mean? It means all of the eigenvalues of Q are greater than or equal to 0. And if you want to check it, I'm not going to have time for a linear algebra debrief today. Maybe there'll be another tools lecture for those who need it. Okay, but you can go into MATLAB or any computational software and do eig of your matrix Q, and it'll return a vector of eigenvalues, lambda. Okay, if they're all greater than or equal to 0, positive semi-definite, it's a convex program. Okay, so that's like the difference. In spirit, it's the multi-variable version of having a cost function that looks like this, for which point you have a clear minimum, and a cost function that looks like this. So let's see. That's when your eigenvalues are greater than 0. Here's when some of your eigenvalues are less than 0. You're going to have some direction where you have multiple minima. And they might be unbounded, might be off in some direction, right? Okay. Okay. That's what a quadratic program is. Okay. So let's do an example with the time that we have. Okay. Example. Okay. So find Q and C for the quadratic objective Michigan, we good, friends? You all, thank you for letting me know when things go wrong. I appreciate it. Doing the best I can here. All right, we've got. So we have some objective function, some cost function, x squared plus 3 times x1, x2. Now make that 4. Plus 2 x2 squared plus 3. Okay. So let's compute our q, which is equal to our second partial derivative of x. Okay. Now we have a decision vector with just 2 variables, x1 and x2. So we're going to have a 2 by 2 matrix, which is our Hessian. Okay. So partial f, partial x squared. Okay. And so that means our first entry is going to be partial f, partial x1 squared. This one's going to be partial f, partial x1, partial x2. This is going to be partial f, partial x2, partial x1. I forgot my squares. Mathematicians will be upset. Partial x2 squared. That's our Hessian. Okay. So our first entry, partial f, partial x1 squared. Got the square there. So our first partial derivative is going to be 2 times x1, right? So it's going to be 2 times x1. Then I'm going to take a second partial derivative to x1. I'm going to cross that out. And it's going to become just the number 2. Then we have partial f, partial. Oh, and I'm probably skipping over a lot of terms. I apologize. Let me just do this a little nicer for you all. Look at this here. I've done this in my head so many times. I skip over all the stuff that's obvious to me. Let's say, what's partial f, partial x1? Well, it's going to be 2 times x1. We agree with that, right? Plus 4 times x2. Plus 0, plus 0. Yeah, I see people getting a little, kill it, get rid of it, you know. Yes, right. Then you have, let's do partial f, partial x2, just from scratch, right? So that's going to be 0, gone, right? That's 4 times x1. Okay. And then that's going to be 4 times x2. And 3 goes gone, right? Sound effects optional. Okay, right? Then if we want to turn this into partial f squared, partial x1, well, this one goes gone, right? So it's just 2. Then we want to turn, if you want instead to do partial f, partial x1, partial x2. Oh, this is going to be gone right now. So this is just 4. Okay. Now we want to get finally partial f squared, partial x2 squared. So gone. This leaves just the 4 associated with this 4. Okay. That means that Q is going to be this nice little matrix. 2, 4, 4, 4. Okay. Okay. Now what's my C matrix? Okay. I made it dull this time. Okay. Very simple. Our C is going to be our gradient of f with respect to x evaluated at x equals 0. Well, we've already computed our first 2 derivatives for our gradient, right? So it's going to be a vector. So 2x plus 1, 2x1 plus 4x2, and then 4x1 plus 4x2. Evaluated at x equals 0. Well, 0, 0, 0, 0, 0. There are no linear terms in this objective function. And you can kind of see that. Let's just, I'll let you write this down here. I hope that my Michigan friends can still hear all this and see all this. Cool. All right. All right. So look at this. What are our quadratic terms? Just count the number of decision variables that are multiplying by themselves or multiplied by other decision variables. Here you have x1 times x1, x1 times x2. So this one is quadratic because x1 times x1. This one's also quadratic because it's a decision variable times a decision variable, x1 times x2, right? There's no plus 3 times x1. If you did, guess where it would show up? It wouldn't show up in the queue because it would get blown away by the second derivative, right? It would show up here though, in the linear terms. Okay, so that's our quadratic and linear terms for a quadratic program. But I know someone is thinking, but Dr. Hubicki, but Christian, what's this? Where did that go? That 3. It's gone, blown away. I heard someone mumble in this room, the 3 doesn't matter for finding all the way up here, for finding x. Whether or not your cost function has a 3 added to it doesn't change what the best solution is. Okay? All right. You know, Christian, what's your best mile time? I won't answer that question. Okay? Christian, what's your best mile time? You know, it's like, what's your best mile time plus 1 million? Who cares? Or more specifically, let's go back to our fence post problem, our fencing problem. Okay. What shape maximizes the area of that fence? Okay, a square. What shape maximizes the area of that fence plus 100? A square. Doesn't change the answer. It changes the objective function value. Where that does matter though, is once you find x star, if you're asked, oh, okay, what's the value of the objective function at that for that solution? You got to remember to plug it back into your objective function if there are constants in it. Okay, that makes sense? Okay. Is it okay that Q is not semi-definite in that example? Meaning, so is the question. Well, it's positive definite, and therefore it's also positive semi-definite. Okay, and we can try to validate that today. Okay, in fact, we got about 10 minutes. I'm going to show you an example by unsharing this screen in just a minute after I get MATLAB open in here. I'm going to show you how awesome MATLAB is in a few minutes at this, okay? Because we didn't check that this Hessian is positive definite or not, or positive semi-definite. Okay, that's the matrix 244, 2444. So we've set up our optimization problem. Now, does this make sense? You know, where does this all come from? I kind of just gave you a bunch of formulas like this is the Hessian, right? This is the gradient. And where is that? How does this all work out? Well, let's plug H and C back into the general QP form. Okay, where my objective function that's going to be minimized is 1/2 x transposed q times x plus c transposed x. Now we know that x is x1, x2. Okay, we've got q, we said is 2, 4, 4, 4. We've got c, which is 0, 0. Okay, all right. So what we're going to do is we're going to rewrite this as 1/2 x transpose. So that's going to be turning that column vector into a row, x1, x2, times a matrix, which has 2, 4, 4, 4, times x1, x2 again. Okay. Plus C transpose, so it's going to be a row of 0, 0, times x1, x2. Be cool? Cool? Okay. Now we're going to do some matrix multiplication. Okay. So we're going to multiply these two matrices first. Okay. It's a 1/2 times a 2/2. Are these compatible matrices? Do we multiply? Yes, we can. Means we didn't screw up because these inner matrix dimensions agree. They're the same. And it's going to yield a 1/2, the outer dimensions, right? Okay. So we're going to run. So what it's going to give us is a 1/2, where the first entry is going to be x1 times 2. So 2x1 plus 4 times x2. That's our first entry. And then our second column, we're going to have 4 times x1, then plus 4 times x2. Make sense? And we're later going to multiply it by x1, x2. Then let's do this matrix multiplication. This will be an easy one. It's going to be 0, x1 plus 0 times x2. No linear terms. Okay. And I'm going to put my 1/2 out front so I don't forget. Okay. All right. I'm going to have my 1/2. Then you're going to have a 1/2 by 2/1. You can do that. 1/2, 2/1. 2's agree. It becomes a 1/1. That's good because the objective function is a scalar. Doing okay, right? So that means we're going to take this first term, parenthesis, 2x1 plus 4x2 times x1. So that's going to give us 2x1 times x1. So that's squared, plus 4 times plus 4 times x2 times x1. So I'm going to write that as x1 times x2 plus 4x1 times x1. So that's 4x1 squared plus 4x1 x2 plus 4. Wait, did I get that right? That's all of them. Yeah. It's all 4 terms. Let's get this right here. Okay. Sure, I got that right. I think I transcribed something wrong here real quick. 4x1, x2. Oh, times x2. This is 4x1, x2. Right? This x should be x2 squared. That should be an x2 squared. There shouldn't. So that should work out. I think I might have screwed something up really quickly, but in my haste here. Isn't Q 2002? No, shouldn't be. Yep, shouldn't be. All right, so then we do the one, then we put the 1/2 in there. We get x squared plus 2 x1 x2 plus 2 x2 squared plus 2 x1 x2. Therefore, x1 squared plus 4 x1 x2 plus 2 x2 squared. Does that look familiar? Hey, that's where it comes from. So I see a question in the chat, should the off diagonal terms be 0? Short answer is no. If you look at Q, the on diagonal terms are going to be associated with the squared terms. Okay, these are your squared terms. And these are going to be your, on the off diagonal, your combined terms. So a good hint is that if you have in here, you will have coefficients associated with like x1 squared, x2 squared, and the off diagonal, you're going to have like x1s times x2s. Times 2 is less than 0. Okay. I see some chat and some talk in the chat real quick. We'll get to that in just a minute. We're going to finish up real fast, okay, and then we'll stop the lecture. I can address this in when the recording is stopped, just so we can make sure we get this correct. So I'm going to unshare the screen here. Stop. I'm going to share this screen with MATLAB. Okay. So for one, we had our matrix, which was 2, 4, 4, 4, Q. You check the eigenvalues of Q. Look at the negative, positive, semi-definite. I must have screwed something up real quick. Let me issue a correction. I think that in my haste, I screwed up my notes here and trying to fix things up. So let's finish up today. And because we have 1 minute left. So yeah, so not positive, semi-definite. But that's the procedure. If you take the Hessian, must have screwed up the Hessian somehow, I guess, but you take the Hessian, it gives you a Q matrix, then that should be, if it's positive semi-definite, then it's going to be the convex. And you can solve it really quickly using a command called, in MATLAB, called quadprog. Okay? All right, so here we go. And what does it take in? It takes in an H matrix, which is the Hessian. Okay, an F, which is your linear constraint matrix, your linear matrix in your terms. Okay, and then your A and your B matrix. Okay, so I'll publish a correction as whatever I screwed up in that process real quick. But yeah, with that, thank you all for your time, and thank you for dealing with the technical difficulties. We'll try to find ways to make that work more reliably. I think I have a few strategies. So thank you for your time.